So in n-gram language modeling, and specifically we are taking up the bigram language modeling or trigram language modeling. Suppose we have this training data, so what problem could arise? In this training data we have the phrase denied the allegations, denied the reports, denied the claims, denied the request, right? But in test data we don't have, and test data we all know that is unseen data, alright, that has never been seen before. So in the test data we have this denied the offer, denied the loan, right? And we want to find out the probability of denied the offer, that is P of offer given denied the. So this probability comes to as 0 because the counts of offer is actually 0, offer along with the denied the. So this is actually count of Wi, count of Wi minus 1 comma Wi divided by count of Wi minus 1. So this is Wi minus 1 is denied the and this is Wi is offer, like so, right? So in the training data this does not occur, right? So this is now 0, and so we are not able to get the probability of some new sentence. So this finally is 0. So some new terms, some new phrase, some new sentences are there, the combination of which is not present in the training data. Alright, so at very we can say the preliminary n-gram language modeling, n-grams work very good when the test data is quite similar to the training data, right? So it works very well. If we are able to find out the probability of denied the allegations, it will definitely give the probability, right? But if the test data is not very much similar or not in line with the training data, then we would have this kind of problem, right? This is the problem of zeros. So how to eliminate this problem, right? So we have bigram probabilities that are assigned 0. Okay, so we cannot also compute the perplexity also, right? So we need to generalize the model so that all these the phrases or words that are not present in the training set can also be calculated by some means. Their probability can also be calculated by some technique, right? So that is called as generalization. So in case of machine learning framework, we have the training data and we have the test data, and test data is that data which is not seen before, and we develop the model in such a way that the model works well for test data also. That is called as generalization, right? And if the model is working well for training data and it is not working good for test data, then we say that the model is overfitting, right? Because the model is not generalizing, it is not going outside the training data, it is not doing well for those data points, for those training examples which are outside the training data. So adding something to the model, some intuition, some heuristics, some techniques, so that the model is able to predict well for the points for training examples that are outside the training data, is called as generalization, right? So there are a lot of techniques for generalization depending upon the problem that we are dealing with. So in case of n-gram language modeling, the generalization is done through the smoothing. So smoothing is actually a technique we will see right now. So in this diagram we see that we have this as the probability distribution of the words, right? So we have suppose the probability of this word given denied the, so we have large number of allegations the count of allegations is large and reports is also larger than claims, request, and something like that. We can assume that in a small corpus we have 3 counts of allegations, 2 counts of reports, 1 count of claim, 1 count of request, and 0 counts of attack, 0 counts of man, and 0 counts of outcome. So when we draw the probability distribution, it means that this is between 0 and 1. So the probability of this allegations is highest, the probability of reports is this much, the probability of so this diagram is also called as probability mass distribution. In case of discrete variables in which we have the things are countable, we call this kind of diagram as the probability mass distribution. So this probability mass distribution is actually, the probability is represented as a function of x is probability of x is equal to something, x is equal to x naught, right? So this function is actually a probability mass function or probability mass distribution. So this can be drawn for a given corpus, right? And we see that the probabilities are 0 here, the attack is 0, the man is 0, the outcome is 0. Now for all those words in which the probability is 0, right? So we have this as the training data, right? And we have this as the training data, so sorry, test data. So we somehow try to make these as non-zero, make these probability mass as non-zero, right? So how could we do? Because the probability distribution mass distribution function says that the sum of all the probabilities, these all should be equal to 1, right? So summation of this all from x0 to xn should all be 0, sorry, so should all be equal to 1. So we cannot just directly put on some mass here, some point, some value here, but what we can do is that we can take out some value from the higher probabilities and just to readjust it with those probabilities which are having 0 values, right? So in this way the overall total probability is equal to 1, or in other terms we can say that the probability mass is same, it's not changed, right? So because we don't have something new added to it, we have only the same corpus, and then we are just readjusting, we are making some assumptions. Now what assumptions are we making, right? So here we are making some assumptions. We are saying that we are giving the 0.5 count to some others, right? 0.5 counts to some others. So how we are giving this 0.5 counts to others, like how is it possible? So we are having this formula, the maximum likelihood estimate of this Wi given Wi minus 1 is this, we all know this. So we say that we have we change this formula and we call the new formula as add one probability or add one estimate, add one bigram probability, and then what we do is that we add 1 to each of these counts. To each of the bigram counts we assume that the bigram has appeared once more, right? So what does it mean? How does it make sense? So suppose this is the bigram table, right? So in this bigram table, whatever test data do I have, right? I can have any kind of test data. I can have either write these previous words. Let me take these. Yeah, attack, man, and outcome. So I'm this. Suppose this is the training data, and initially we all had these as zeros, right? We all had these as zeros. All these, in place of ones we had zeros. right? So we assume that all the let's compare it with the previous table. Yeah, right, this is the table. So we see this is 5 2 2 0 1 15, right? And in our table, the new one, it is 6 3 3. So initially we had 5 2 2 0 1 15 2 1, right? So we assume that each bigram, that is this I is occurring once more, right? So this 5 plus 1 becomes 6, want I becomes 2 plus 1 as 3. Similarly, eat and I as a bigram was initially not present in the corpus. Now by assuming it that each of these bigram is appearing at least once, so those bigrams that have not been appeared in the data, they will be appearing as once, right? So this is the assumption. So we don't just to take care of that only these non positive or zero bigrams zero bigram counts are appearing only once, but we assume that all the counts are appearing as once, right? Appearing once more. So for those that are not occurring, it will be from change from 0 to 1. For those which are occurring, it will be adding 1 to all these. So in this case, we see that this initial count is actually is the V, is mod of V, right? The total vocabulary. This is the total vocabulary. So this count of total vocabulary is V, right? And this total count is the bigram count, right? So bigram count, this is when we add, this is the bigram count for I with all the other words, right? So the bigram count of I with respect to all the other words will be increased to bigram its original count plus the total number of words, right? So whatever is now the new word, whether it is in the training corpus or not, we just make an assumption. We can have we can have these three words here: attack, man, and outcome. So I'm having attack, man, and outcome. So I will add these as ones. Initially it was zeros, and now my new count will be again these original one plus all the vocabulary, the new vocabulary, right? So in this way we can change this original formula. We can change this one, this original formula to be, we are just for the given that particular combination of bigram Wi and Wi minus 1, we just add 1 for its count, right? And we divide it by the count of the preceding word, and we add V to all, to the count of V, to the count of the preceding word, right? So the count of this preceding word is the count of this I, right? So for this bigram, suppose I am considering want 2. So the count of want 2 is increased from 608 plus 1 to 609, right? And the count of the preceding word is want. The count of want is the count of want 2. By adding 1, it becomes 609, and count of want is equal to 60, not 608, but all these, its original count C wi minus 1 count of wi minus 1 plus the new vocabulary, right? So in this way the formula is changed now, this one, right? You can now see that how we are changing the formula. So these are the new probabilities, and we see that we don't have any of these probabilities as zero probability, right? So whatever these are not, these were not occurring in the corpus, so it is not present in the corpus, so that will not make it not make the probability as zero. Initially this term had been 0, but by adding 1 we will get at least some probability, at least 1 by something for those counts which were 0, 1 by some number, right? So the probability becomes non-zero, and we call this technique as smoothing. And when we use the adding 1 in the numerator and adding v in the denominator, we call it as Laplace smoothing, right? So this is the new Laplace probability, Laplace bigram probability. And now how to get back the counts, right? How to get back the count? We are directly calculating the probabilities and we are changing the counts. Now what could be the counts that correspond to this probability table, right? What could be the counts? So in initial this initial probability formula, we see that we are having the probability by dividing it by this term, right? And this is the count. This C wi minus 1 comma wi is the count that is filled in the count bigram count table. So this Cwi comma wi minus 1 comma wi is actually this counts table, right? So when we multiply it with the original number of counts, this one, we get the Laplace counts, right? So we get these modified counts that are corresponding to this probability, right? So we are having these as probabilities, and these are the reconstituted counts. We call them as reconstituted counts, right? So on the basis of the number of the size of corpus, we can reconstitute the counts. So in this way we get the non-zero counts here. So by this probability we see that we are having the non-zero probabilities, and then we are having the non-zero counts as well, right? So this technique is called as smoothing. And when we compare this, we see that how the probability mass has been transferred, the probability of the counts of I has been transferred to all those non-zero, right? So this, from here also something has been transferred here, from here also something has been transferred here, from this also something has been transferred to this, right? So this is the original bigram count, and these are the Laplace counts, right? So this is add 1 smoothing, which makes things a little bit more working, and the test data on which that is not present in the training data. So this add 1 smoothing allows us to make those counts non-zero, and we are able, the language model is able to work. But we have some other techniques also that are much more efficient than Laplace smoothing, and we will see them later.